is a work that I did with some colleagues from France, Cyril and Rodrigo. Cyril was a postdoc at Manuel. So that's a big nice to try to remember some things that I was planning to write before, but I think home will not be able to see. There is a lot of notation. The letters, we try to use letters that make sense in the context, but let me start telling you what this is all about. So, in financial and actuarial risk management, which is the kind of stuff I do, it's very important to deal with the dependence of a vector. Right? So the vector for us will be x. And one of the standard things to do is to use a copula model. I have some set of slides explaining what a copula model is, to feel like there's a problem to talk about this. But let's go through and if I need it, like that. And so it's very common to use copula models, but the drawback of trying to use copula models is that most of the parametric copula models are not suitable for high dimension. By high dimensions here, I mean something larger than 5 or 6. Right? Most of the simple copula models do not work very well for dimensions that are reasonably. So the setup is something like this. We are interested in computing expectations like this, expectation of a function of a random variable, or expectation of a function of the random variable conditional on the random variable being some set A. Okay, so the model for us, and this is the first thing to remember, the model is X vector, has some distribution C, which is the complement of F1, which is the marginal of X, and Fd, which is the marginal of the D component of the vector X. Okay? So what is the problem here? So if we are in the second case where we want to compute the expectation of G of X, conditional on A being some specific set, if this event on the right is rare, trying to do IID sample in one time will be very inefficient, right? Because you sample a lot, throw a lot of samples away, and this will be completely discarded. So what we'll try to do, what I'm going to present to you today is do some MCMC. Okay? So this is pretty standard. You can do some MCMC to reach the rare event, and this is not a big deal. I think what is interesting from this paper is the model we are going to use. This is the model, particularly the model for the complex itself. Okay, so just to give an idea of the kind of stuff we want to compute. So we have these 3 dependence measures, or 3 statistics, let's say. One is the tail dependence that people may know about, the semi-correlation, the k-expected shortfall, which is the one I'm going to focus today. So just quickly here, the semi-correlation is very easy. So the correlation between 2 components of the vector x, when the components are larger than 0 or smaller than 0, or whatever you want to put on the left. But what I'm going to focus today is on this one, k-expected shortfall, which is this. So you look at the k-expected shortfall. Going back to where I was, so I was saying that we're going to focus today on the k-expected shortfall, which is a measure of is the expected value of a random variable, and this random variable x for me will denote losses, financial losses. So the larger x, the worse. So x large is something really bad. And I'm looking at the expectation of x conditional on the fact that out of my D assets in the portfolio, at least k of them had losses larger than C. C may not be a good letter here, but any constant. Okay, so imagine this. So you have 1,000 assets, you look at k is equal to 100, and you want to know what is the expected loss of one of your assets when at least 10 of them, you don't know which one of them, at least 10 of them or 100 of them had losses larger than 5% or 1% or something like this. Okay, so that's the kind of measure that I'll focus on today. Okay, so the model itself. So the model is the following. So in this paper by O and Petto in 2017, there was a copula that's an interesting model. So the model is based on an auxiliary variable, y. So y is a vector. So y is a vector. That's a function of another vector that's called z, sorry. So phi is a function that goes from R capital D to R small d. And y is the vector that we're going to construct just to extract the copula from that. Okay, so the idea is this. It's like a factor model, for those who know factor models from economics, very simple thing. So z is a vector with n and epsilon components. So we have j components of n and d components of epsilon in the following way. Sorry, n is a vector of factors. So capital J will be a number that's much smaller than small d.
So if I have D observations, I'll have J to be, I don't know, in our examples here, for example, 2 or 3, 5, 6. And epsilon are the idiosyncratic errors. Okay, so each one of the observations will have one idiosyncratic error. Each one of the components on the vector will have one idiosyncratic error of their own. So the full vector Z of M and epsilon is completely independent. So everything is independent of everything else. But I'm also going to assume that epsilon is an IID sequence. Okay, it's just an idiosyncratic error, as usually to be IID. So for example, just to be very simple here, the simplest, as simple as possible. So Y is the sum of one factor that I'm calling M and one idiosyncratic component for each one of the components of Y. So Y is M plus epsilon I, Yi is M plus epsilon Y, where M can have any kind of distribution and epsilon the same, right? So let's say that M is a skew T distribution, and I'll explain why I'm using this kind of distributions later. And epsilon is, for example, ID, a T distribution, okay? So what happens when I do that? If I do that, I will have an implicit copula defined by this model, because, for example, here in this case, I have one factor that's present in every single component of my vector. So they're all dependent, x, y1 up to yd forms a vector that's dependent. And the dependence comes from the M, okay? But what is the deal here? The deal is that the distribution of the sum of M and epsilon Y in this case, or the distribution of Y, is not something that you will likely know. In this simple example, there are two simple distributions. I don't know what is the distribution of Y. I don't know what is the distribution of a skew T and a T. Maybe this is doable, but let's assume that maybe harder. Okay? So, but what I don't know is what is the distribution of Y. That's the assumption that we'll be working on. And I will say that Y as a vector has a distribution that's given by a copula C with marginals G, where G is in red because I don't know G. I don't necessarily know G. But what I want to model is not Y, it's X. So I know the marginals of X, which are F1 to Fd. I know exactly how to define these marginals. I know to play around, how to play around with these guys, but I don't know how to play around with G's. Okay, but I will use the copula that's induced by the model in Y into the model of X. Okay, I'll spend one more minute on this because I think this is the most important basic thing for today. So I will create a surrogate model if you want, which is a model for Y, from which I will just take the copula. I will not use the marginals that will come from this model. I'll just take the copula and say, okay, this is the copula that I want to use in X. Why so? Because this is a simple model. If you look at this, it's just a sum of a component plus another random variable, a fixed component plus another component that is different for different parts of the vector. Okay, so Y is something that has copula C. X has also copula C, but the one that creates the copula is Y, not X. Okay. So what is the problem then? The problem is that I have a vector X, X1 to XD there, with copula C, marginals F, and I want to compute the expectation of a test function G, conditional on X being some set A. And this will approximate by Monte Carlo samples that will take the average in N of G of XK, something like this. Okay, and the question is, what is the convergence rate of this thing here, the Monte Carlo average to the true expectation that I want to compute. So in the paper that I mentioned earlier, the OM pattern in 2017, they have a very interesting model for the S&P 100. So they say that the surrogate model, the Y, is a component. I'll talk about this model later again, but the Yi, each one of the components in the surrogate model, is given by a beta multiplied by a factor M that doesn't change with the component I, plus a gamma multiplied by a factor that depends on the component I, plus an idiosyncratic error. We'll see later that this is to be seen, M naught is to be seen as a market factor, and MSI is a market factor, a sector-specific noise. Okay, so we have two different components there. But we can do the same thing, right? So Y is the sum of some random variables. M naught has skew T distribution. The other M's has T distribution. And the epsilons also have T distribution. So in the end, I don't know the G. I don't know the c.d.f of Y. And I want to compute the expected decay, expected shortfall for X, not for Y. So I'll take the copula of these guys here, using the model that I know the marginals, which are F, and make this a model for X. Yeah, a lot of letters to remember. And there will be more.
Check, sorry,
Yes.
very naive question. What is X?
Again, X, imagine that SX are my financial losses.
So I understood that, but I'm
but-
saying in the example of the S&P 100.
Oh, okay. So I haven't said anything about the X. I just said about the copula itself.
Oh, I see. Okay.
Okay.
So they constructed this copula.
I'm just focusing on the copula. So
All
when I go back to the example, I'll do everything and talk about the marginals as well. But now the focus is on the copula. Okay. So how would be an algorithm to sample from X? It would be very simple if we had access to the marginals of Y. So the algorithm would be this. So you sample Z, which is a idiosyncratic factors epsilon and the factors M. You compute Y, which is a transformation of these guys. For example, in my example, it was M plus epsilon Y for each one of the components of Y. So my phi function is very simple. From this Y sample, I get my uniforms to define the copula, right? So U is a vector of U1 to UD. And I would just apply the marginal c.d.f to one of each of the marginals, right? So G1 of Y1 has uniform distribution, GD of YD has uniform distribution, and they all together have the copula that I'm interested on because I sampled Y through my model. They are not independent, remember, because in my example, I had the M that was the same for all across the components of Y. How do I get the X, which is what Joanna was mentioning? So now, if I know the marginal of X, the marginal that I want to input in my model, if my marginal is Fi, I just use the inverse c.d.f of X and apply it to U. So Fi minus 1 applied to Ui will have distribution marginally Fi and condition and jointly will have copula C as I wanted. So what is the problem here? The problem is that I don't have access to G. G is not something that will be known because I may construct a model that's hard to find out what G is. In my example, if M is skew T and epsilon is T, I may be in trouble, right? So that's the kind of problem that we're going to deal with. There is this schematic thing here that I don't think I'll go through. I think I've repeated many times what we're doing. Yeah.
So this is how you would sample, right, from a distribution for X based on knowing parameters for the distributions for M and epsilon, right?
Yes, exactly.
So
So
you want, or do you want to do inference?
I'll make this very clear, which I should have done earlier. I'm not doing any inference on this.
Okay.
All I want to do is to compute the expectation. Let's assume that I've done the inference before.
Okay.
That's something that we'll find out how to do, but there are some ways to do inference. That's what the 2017 paper by Owen Pat was about. Let's say that we have all the distributions known, all the distributions are known nicely. I know all the parameters there. Okay. So my main interest, the only interest I have is to compute the expectation of a function of X, conditional to something. Okay. Cool. So what could I do? What can I actually do? So I cannot use G because G is unknown. It's possibly unknown. So what I will do is the following. So I'll use the same inputs, but only the things I know. I'll use the inverse c.d.f of Xi, and I will construct a Markov chain on X. Right? So what I'll do is the following. So for each one of the iterations in a Markov chain, which is K, so K is the iteration on a Markov chain, I will sample my Z from a Markov kernel P. So I'll sample Zk given Zk minus 1. I will transform the Zs, which are the M's and Epsilons, to Y. I'll have then a Markov chain in Y. And I'll create from this Markov chain, I'll create an approximation for the marginal distribution, marginal c.d.f of Y. How? I'll call this instead of G, I'll call this G tilde, index under by K, where K is the iteration of the Markov chain. So G tilde is an approximation for G without the tilde, which is the true marginal distribution of Y. So how do I construct this approximation? So forget about these first two terms here. So forget about this term here for a second and this term here, and just look at this. So all I'm doing is to compute the empirical c.d.f based on the samples along the chain. So I'm taking a time average to compute this empirical distribution in Y. So once again, I sample from Z, I transform Z to Y. So the Markov chain is running Z. The Markov chain gives us a Markov chain in Y. And with this Markov chain, I construct an empirical approximation for the c.d.f of Y. So this approximation will get better and better if my Markov chain is convergent. And I'll define some other quantities here that you'll probably forget in 5 seconds. But let me try to make you remember. So V is kind of a U. So U is the uniform that comes from the copula. But V is the uniform you get, which is not uniform actually, is a kind of uniform you get when you don't apply the true G. You apply the empirical G that you're getting from the Markov chain. So this should be close to U. And if this is close to the true U, if you apply the F, you get the true X. So if you apply F minus 1 to V, it should give something that's close to the true X. So I'm calling this X anyway. And this is X indexed by K. So this is a Markov chain X as well. Okay. So what I want to show is that if I keep on if I use this kind of scheme, I will eventually get a Markov chain in X that converges to the true distribution of X. Okay, so that's the game. And why am I using Markov chains for these things? Remember that I want to sample X conditional on a rare event. And to do this efficiently, it doesn't look like a good way to do is to do that. Maybe a bit harder to understand exactly what's going on, but the idea is simple, that I want to sample from a distribution conditional on something else. And in order to make this efficient, I'm going to use a Markov chain that will go faster towards that rare event there. Okay, so I said that we could forget these 2 terms here. For those who know, this is just a modification of my c.d.f, just to make sure that it's not getting neither to 0 nor to 1. Okay, otherwise this will explode to minus or plus infinity when I transform with the inverse c.d.f. So remember that this modification is getting smaller and smaller the longer I run the chain, right? So when k goes to infinity, the first term will disappear, the second term will disappear as well to go to 1. Okay, so the longer I run the chain, the closer I'm getting to approximate G in the whole interval.
So is that just a problem when the support of X is like unbounded?
Yeah, yeah. And that's what I want, right? So I want X. If we remember, I want X to be my financial losses, the percentage losses, like the returns. And I want this to be minus or plus infinity, right? I don't want this to be bounded. But if it was bounded, it would be easier here. Okay. And okay, so I don't have U, I have V. And I can also define something else, but this is just for some of the proofs. We can also define what is a W, which is the true G, but not applying in the true Y, but applying in the Y that came from the Markov chain. Okay, so this I'll call W. So U is the true, V is the one that comes from the modified c.d.f from the Markov chain, and W is something that comes from the true c.d.f, but on the wrong, let's say, quote unquote, wrong Y, but the Y that came from the Markov chain. So what I'm going to show you is that what I hope so far, just hope, is that U is close to V. V is something that I can compute, and I want V to be close to U, and then X will be close to XK.
So the first 2 steps of this loop, right, the ZK from P, ZK minus 1, and then computing YK, that's the Markov chain.
That's the Markov chain. That's the Markov chain. So Z from P of ZK minus 1 dot, that P is my Markov kernel that will move Z's.
So why don't you use all the N samples? Why do you do the G step 3 sequentially? Why wouldn't you just once using all N samples estimate the empirical c.d.f?
Now, I'm using all. I may have misunderstood what you said, but what we are doing is to use the samples from the very first sample of the Markov chain up to the point where we are. So K goes from 1 to capital to
K is iteration.
K is the iteration of the Markov chain.
Yeah, so my question is why can't you just do that, the second steps offline after you've done everything? You just do a Markov chains only as a Z, and then you're transforming Z into Y. And you just take all the Y's.
I see. You mean you okay? Yes, probably. So let me think about this. So
Does step one depend on steps 2 and 5?
I think
in
step
any
one,
way?
it looks like step
it
one.
will, because,
Okay.
okay, so what will happen is that when I move along the chain, I want to make sure that, probably this is not a problem here, but I want to make sure that I'm reaching a rare event.
Uh-huh.
So to know if I'm getting closer to the rare event, I need to know where I was. And
Okay, so somehow maybe in P is some information from
Yeah.
3 to 5.
Yes, but I'm not so sure now. But let me move and then I'll try to get back to this. But once again, I have a Markov chain in Z, we'll define a Markov chain in Y, and I'll do a transformation and this will define a Markov chain in X. Okay. And the kind of stuff that we're able to prove under some assumptions that I can very quickly go through is some of these convergence rates. So the assumptions are mostly reasonable. Some of them are just technical that I don't think I'll go through them. But for example, the first one is that G is continuous. That's easy. What I'm going to assume that may be strong, but we prove in our examples is that we'll take a kernel P that's geometrically ergodic, and this is geometrically ergodic in the Z. So this is easier to control. We assume that there is an index here such that this quantity here is bounded in the L norm, where L is the Lyapunov function from that geometrically ergodic function, geometrically ergodic kernel P. And the meaning here, the heuristic, which is very loose, is to say that whenever we have this Q max very close to -1, it's equivalent of having the V's, which is not the U, it's the U with the G tilde, having more negative moments. And we need this to prove some of the convergence from G tilde to G. So we assume that this function here is continuous and what this function is all about. So phi, and I'll need this in a minute. So phi is a function that's the composition of G, which is our test function, and F1, Fi, Fd inverse. So let's see what happens when I apply phi to something. So phi will apply to U, which is something that has the copula C. When I apply phi to U, I'll apply F1 minus 1 to U1. This will be X1. This will be XD. And when I compose this with G, this will be G of the vector X. So this function here, phi, is just a function that computes G of X, but using the uniforms instead of X. Okay. So phi is a function that takes uniforms and returns you G of X. So the last assumption is the one that's even harder to understand, and this is not, I'm not going to try much on this. It's just a technical assumption on the functions phi. But the heuristic again is that the larger is this parameter alpha, the heavier are the tails of X. We have some examples on this, on things that we can compute these things explicitly. It's just a simple Pareto example. So the main results of this, and I think this is, I'll try to make this understandable. So the first result we have is that G tilde gets close to G, and we have the rate in which they're getting close to each other. So remember, G tilde N is the approximation along the chain, along the Markov chain. And when I increase G, when I increase N, sorry, I'm getting close to the true distribution G. Remember, if I had an IID sampler, if my Z was an IID, was being sampled IID, that would be trivial, right? I would know exactly what would happen. Because I'm just taking an average of IID samples, and then I'll get to the right distribution with the empirical distribution. Well, what's going on here is that I'm running this through a Markov chain, and I'm taking the Markov chain to help me improve the c.d.f, the marginal c.d.f. And we have the actual rates there. So the other theorem that we have is that if we apply the function phi to N, to V, or to W, they're getting close as well. So remember that phi is essentially G, is essentially the test function. Okay, so if I'm applying phi to V, which is something that I can actually compute, so V is G tilde of Y, I can compute this guy. I cannot compute W when I'm running the Markov chain because I don't know the G. W is G of Y. V is G tilde of Y. I know that these two guys are getting closer. I know the rate, and that's the second result. But the ones we care more are the ones that are here, right? So we have some weak convergence result, which is the expectation of G of Xn. So Xn is the Markov chain, is getting close to the expectation of G. Okay, but the problem is I don't know how to compute this guy, right? So I don't know how to compute the true expectation of G along the Markov chain. We know the rates, but we don't know how to compute this guy. So in the end, we have the convergence of Monte Carlo average, right? So we know that the empirical average of G along the chain is converging indeed to the expectation of G of X. And we know exactly the rates in which they are converged. Depends on that Q max and alpha, things that I didn't talk much about. Okay, so that's more or less that. These are the main results, but this doesn't quite solve the problem that we started with, right? So the problem we started with is we wanted to compute the expectation conditional on some event A. This is a bit harder, but the main idea is there already. So it's a bit harder, but it's just a bit messier, not harder. So let's say that our event A is an event that depends on X, right? So A is, I'm talking about my vector X, but I can also, let's say that I can also work out this event A as a function of the random variable Y or as a function of the random variable Z. So AY and AZ, I'll say that these are sets that I know exactly, which may be harder for some of the examples I showed. But in the K expected shortfall, this works out nicely. So what is the problem here? Whenever I have a conditional distribution on X whenever I'm targeting a conditional distribution on X, I will unfortunately need not just the conditional distribution in Y, but the unconditional distribution in Y as well. And I'll show you why. So just remember that the base formula will give you something like this. So if G is the marginal of Y, I can write this as something like this. I can write this as the c.d.f of Y conditional on A times the probability of the event A plus the other term that's Y given A complementary and probability of A complementary. So remember that this guy is small, right? So if this A is a rare event, P of A is small, and P of A complement is large. So this guy here is not a big problem, right? Computing the c.d.f of Y, given that I'm not in the set that's rare, that's easy. That's not a problem. The problem is here, which is the problem that we are trying to solve with the MCMC. Now the big algorithm, which is essentially what we did before. So the algorithm is one algorithm for sampling from the conditional distribution of X given A, sampling from the conditional distribution of Z, and Z in A and Z not in A. So how do we do that? We sample a Markov chain ZK A, which is a Markov chain that I'm trying to reach the set A, and I sample another Markov chain that's trying to reach the set A complementary. For the second Markov chain, as I said, it can be very simple. It can be just IID samples. Because if A is rare, A complementary is not rare. So I use just IID sample for the second one. But in theory, I could use any Markov chain. So I run the Z Markov chain. With the Z Markov chain, either the A or the A complement, I compute the Y. YKA or YKA complement. Just doing the transformation file. Now I approximate and modify my function G. So this in light blue is the approximation for my c.d.f conditional on the event A. This in darker blue is the c.d.f conditional on the event A complementary. But I also need to compute the probability of A and A complementary. So what we are doing so far is to assume that we do this offline. So we do a bunch of samples from X, not very correctly, but we approximate this as well as we can with a large sample. We compute this probability and we move on, pretending we know A and A complementary. So that's a reasonably large assumption. But we could work this out, but I think it gets much worse. So let's go back to the true example and we finish after we talk about this example and show you some results. So once again, Xi denotes the losses of the ith stock. So X large is bad, X small is good. So we have D equals to 90. We have 90 stocks in our portfolio or things that we can trade. So the K expected shortfall of the ith asset is the expectation of the ith loss, conditional on the fact that all the assets were had losses larger than C. Okay, so I'm looking at one of the quantities, I don't even remember the name. So I'm looking now at all components of my vector having losses larger than C. What is the expected value of one of the components, of each one of the components? Okay, so this is a very stressed out scenario. In the examples, we're going to say that C is equal to 1%. So we are saying that we have 90 assets that in one particular day are down by 1%. That's very unlikely, and the probability of a rough estimate of this probability is something like 10 to the minus 4. Okay, so we do 10 to the 6 samples of Y to have an estimate of this, that's the order of 10 to the minus 4. But once again, this is very approximate. That's not the best thing in the work, because this is not a perfect sample. So the model again is the kind of linear model that I talked before. So Xi will have marginals that are T distribution. So this is easy. I look at my time series of each one of the assets individually. I ignore all the others, and I model them as a T distribution. So Mi, Si, and Ui are things that were estimated beforehand. MLE, it doesn't matter how I did them. Not going to touch that today. Yi, which is my surrogate model, will be that thing that I mentioned before. So it's a beta multiplied by a M naught, which is my market-wide factor. So beta Si is the component for sector I. So sector is the sector, the industry group of my assets. So I'm modeling with 7 industry groups. So there are 7 different betas. There are 7 different gammas, and there are 90 epsilons, for example. So I have a market-wide factor, I have an industry group, I have a sector-specific factor, which is the M of S, and I have the idiosyncratic noise, which is epsilon. Once again, all the M's and epsilons are all independent, and the epsilons are IID. Just some notation there with D, J, and capital D. So how do we sample this? If it was not convoluted enough, we'll do one more trick, and I promise this is the last. So we'll sample Z using a Markov chain using preconditional Crank-Nicholson. So how are we going to do that? So we are going to construct a Markov chain in a random variable that's Gaussian. So Z will be a Gaussian random variable that I'll try to get samples from that restricted to some set A of Z. So after I get these samples, I'll transform back, and I'll get to my X condition on the right set. So preconditional Crank-Nicholson sampler, for those who don't know, it's here. Don't want to talk too much about this. But I have my sampler, and I think the main message here is that I'm not running the sample in Z's, in the M's and epsilons. I'm running the sampler in a Gaussian universe, just to make my sampler easier to look at. So if Z is something that's Gaussian, I'll call F of N the c.d.f of a Gaussian, because I couldn't use phi anymore because phi is something else. So Fn is the c.d.f of the Gaussian. I'll apply Fn to Z1, which was also a Gaussian. So this thing will be uniform. Fn of Z1 is uniform. Fn of Zi plus 1, I plus j, all these guys are uniform, right? So after I do that, I will compose this with the inverse c.d.f of the thing that I want. So remember that I said that M naught, Mi, and epsilon I had some specific distributions, which are the ones I want. So skew T, whatever. Okay. So to get to these distributions, I'll sample from a uniform. I'll apply the c.d.f of the uniform and then the inverse c.d.f of these guys, just because I want to do my sampler in the Gaussian universe. Okay, so just to finish, my Y is the function phi. The function phi is kind of simple, right? The function phi is just take the beta, multiply by the M, take the gamma, multiply by the other M, and take the nothing, and this is your epsilon. So this is Gaussian. Gaussian, I apply the inverse c.d.f of a T distribution. So this term is what I'm calling epsilon, which is the idiosyncratic factor. And the same thing for the other terms over there. Okay, so this will build up my model, and this is the result. So what am I showing here? And this is worth a couple of minutes explaining what's being shown here. So I'm computing the K expected shortfall, which is expectation of Xi, given that everything else is larger than some constant. The constant was 1%, right? So each one of the colors, first the colors, blue, red, and black. These colors are each one of the marginals that I chose. Marginal 1, 2, and 3, doesn't matter. Okay, so in blue, the dashed line in blue is the true, quote unquote, expectation of X3, given that everything else is larger than 1%. The other one is the expectation of x2, and the other one is expectation of x3. So how does this work? So you see that there is something very clear, that the samples are getting wider and wider, right? So there is clearly something going on here, right? So each one of the light colors, so there are 3 chains for each color. So light black means one Markov chain. So this is time of the Markov chain. Light black is one of the chains. I have 3 different chains, or even more. I don't quite remember, to be honest. And the dark black chain is the average at each point in time of 3 chains, 3 different chains. So for each one of the chains, I think here it's quite clear to see there is 1, 2, 3, 4, 5 chains at least. Why do I know there are 5 chains? Because I know that the modification is different for each one of them, right? So whenever I go longer in the chain, I'm getting something that's exploring more and more the space. Before, when I start the Markov chain, I'm not allowed, because my G tilde is not allowed to go to plus or minus infinity. Okay, so whenever I run along the chain, I can increase the space that I'm exploring. But it doesn't matter that much, right? Because you can see that around here, you are getting sufficiently close to the right result, even though you haven't been allowed to explore the whole space by the G tilde. And the same happens to the other marginals, but we cannot see because now they are all together. But at least the red one, we can see the same kind of effect, and the blue one is hidden behind everything else. And so just to conclude, so we studied some theoretical and numerical properties of something that we call the transform MCMC, because there are so many transformations that we thought that this was a reasonable name. And the scheme is somehow developed to be efficient to compute expectations and conditional expectations given some rare events, in which the distribution, the joint distribution of what you're trying to compute expectations of is given by these factor copulas that I tried to explain today. We have some mild and natural hypotheses, some mild, some natural. I'm not going to say they're all natural or mild. And then we can get the convergence rate of all the estimators we did. Then we went back, we revisited this financial risk management example, which is the one that I mentioned with the factor T, skill T copula. This was done in that 2017 paper. Oh, by done, I mean that people actually did the estimation using MLE and try to compute the quantity there, the K expected shortfall, but through a completely different route. So what's next out of this? I think the obvious question is how the hell do I do inference for these guys? The original paper does simulated method of moments. We're trying to adapt that to do some approximate Bayesian computation for these guys. And I think that's where we stand now. And I think I'll stop here. Thanks a lot for the attention. Sorry for those at home with the problems in the mic, but that's it.